Hello all. Today we'll see the next topic, that is reducible to exact differential equation. So in previous lecture we saw the exact differential equation. So exact differential equation are nothing but the differential equation which are perfect derivative of some function. Then we saw the condition of exactness, when we can say that the given differential equation is exact. When the differential equations are exact, we can find its solution using the formula of general solution. So these things we have studied in our previous video. Today, we'll see the case when the differential equations are not exact. So this is called the equations reducible to exact. So here, what we are going to do, we are going to make the differential equation exact which are not exact, and by using some factor we are going to make it exact. So for this, first of all, we should know the concept of integrating factor. Integrating factor. So what is integrating factor? Integrating factor is an multiplying factor by which our equation can be made exact. Suppose we are having differential equation like this: m dx, m is function of x and y, and dy, which is equals to 0. And we have observed here that dou m upon dou y is not equal to dou n upon dou x, means our given differential equation is not exact. As it is not exact, we have to use this concept of integrating factor. So suppose k is our integrating factor, k is some function. So if I will multiply my function or differential equation m dx plus n dy is equals to 0 with k, then now this will become exact. How will you identify it will become exact? By checking dou m upon dou y equals to dou n upon dou x. So integrating factor is an multiplying factor by which your equation can be made exact. So how to find this integrating factor? So there are 4 cases to find this integrating factor. So in today's lecture, we'll see how we can reduce our function into exact form, which are non-exact. So the first rule for this is, let's start with new. So rule 1. So rule 1 is when you're having the mx plus ny, m is coefficient of dx plus ny, n is coefficient of dy. If this is not equal to 0, and the given differential equation, means whatever equation given to us is homogeneous. What do you mean by homogeneous? Homogeneous equations are nothing but where each term will have same power. For example, if you are having this equation x square plus 2xy plus y square is equals to 0. You can observe here that x is having power 2. Here x is having power 1, y is having power 1. So 1 plus 1, 2. And y square. So again power 2. So each term is having power 2. So this is homogeneous differential equation. Now can you tell me, is this homogeneous differential equation? Yes, this is homogeneous differential equation again. Its power is 3. Here 2 plus 1, 3. Again 3. So this is homogeneous differential equation, sorry, not differential, it's normal equation, homogeneous equation of order 3. Now check this. Is it homogeneous? No, this is not homogeneous as here power is 3 and second term is having power 2. So what is rule number 1 applicable for? When your differential equation is homogeneous and you are having mx, m is coefficient of dx, n is coefficient of dy. If it is not equal to 0, then what will be the integrating factor? So in this case, integrating factor will be equal to 1 upon xm plus yn. So you will multiply, suppose this is your k, and multiply by these two your given differential equation and your equation will become exact. Then solve it by using a regular process of exact differential equation. So remember, rule number 1 is applicable when mx plus ny is not equal to 0 and differential equation is a homogeneous differential equation. Now rule number 2. So rule 2 is applicable when your differential equation is of the form y some function f1 of xy y dx plus some function f2 of xy x dy is equal to 0, means your m will be such that you can take out common y. Your n will be such that you can take out common x. If you're having this y dx and x dy form, and also this mx minus ny is not equal to 0, then integrating factor for such differential equation will be 1 upon mx minus ny. Now multiply by this integrating factor to given differential equation and make it exact. Then find the solution using general solution formula of exact differential equation. Now let's move to the rule number 3. Rule 3. So rule 3 is for rest of all the equations where you can find the differential equation non-exact. So if given differential equation is not homogeneous, if you are not able to write it in terms of y dx and x dy, then obviously rule 1 and 2 won't be applicable. So move to the rule number 3 and 4. So rule 3 is like this. You're going to find this dou m upon dou y and dou n upon dou x for checking whether it is exact or not. So take its difference and divide it by n. N is nothing but coefficient of dy, and you will get it as a function of x. Then the integrating factor for this will be, integrating factor will be equal to e raised to whatever this f of x you will get, take its integration with respect to x. So this is applicable when it is not homogeneous, as well as you are not able to write your differential equation in terms of y dx and x dy. Now rule 4 is similar to this. Either of this you can use depending on by which your difference of these two derivatives is divisible by. Suppose it is divisible by m. So m's derivative should be subtracted from n's derivative. And obviously you're going to get here g of y, the function in terms of y. Then the integrating factor will be equal to e raised to integration of g of x, no, sorry, g of y dy. So whatever answer of this e raised to g of y dy will be there, that will be integrating factor. So just let's recall, rule number 1 is applicable when your differential equation is homogeneous. Second is when your differential equation is like this, y dx and something into x dy equal to 0. Third and fourth rule will be applicable depending on whether the difference of these derivatives is divisible by n or divisible by m. From that, you can get the f of x in this case and here g of y in this case. And then integrating factor will be e raised to integration of f of x dx. And here integrating factor will be e raised to integration of g of y dy. So in this way, you can identify the example pattern and accordingly use the exact differential rule, rule for finding the integrating factor. So in this lecture, we saw the examples of differential equation reducible to exact, which are non-exact. So in our next video, we'll see some examples of reducible to exact rule by rule. So thank you all of you.